Hello, beautiful people. Welcome to Rose Academy. In this tutorial, we're going to be looking at the amplitude, or also known as the argument of a complex number. In the last tutorial, we look at the complex conjugate and also the modulus of a complex number. And in this tutorial, we're going to be looking at the amplitude or the argument of a complex number. Before we dive mainly into the examples and also the exercises we're going to be looking at in this tutorial, we're going to start by revisiting what we look at the beginning of this series, which is Introduction to Complex Number. Back then, we look at the complex plane and also the normal real axis plane. So I would like to bring that graph back. So if you are looking at complex number and we have to plot complex number on a plane, we look at the real plane and also the imaginary axis. So this is the real axis, this is the complex number axis, and we have the imaginary axis. So we look at this at the beginning of this tutorial. We look at this as the real axis and also the y-axis as the imaginary axis. So for example, if you are given a complex number z1 equal to 2 plus 3i, and we have to represent this on this plane. So we are going to come to the real, don't forget 2 is the real part, while 3 is the imaginary part, and I is the imaginary number, just like we said in the last tutorial. If you have to represent this on this plane, the complex number z equal to 2 plus 3i on this complex, let me just put this here, complex plane. So we come to the real axis, which is the x-axis, this is 2, and we come to the imaginary axis, which is the y-axis, so this is 3i. So we can plot this. So plotting this, we have z1 here, which is equal to 2 plus 3i. So this is just a brief revisit into the complex plane, where we look at the imaginary axis and also the real axis. So we are going to be dwelling on this fact majorly in this tutorial, where we'll be looking at the amplitude and also the arguments of a complex number. So before we start looking at some examples, I would like to give some definitions. We define the positive angle between the complex number z equal to ix plus iy and the positive real axis as the amplitude of a complex number. It's simply the angle between the imaginary part and also the real axis. So if you have, let me put this on another graph. So if we have the Argand diagram, and we have this is the real axis and this is the imaginary axis. So we have our angle z, we have complex number z1 to be equal to 2 plus 3i, just like we've seen before. So this is 2 and this is 3i. So this angle is the amplitude or the argument of the complex number. There are some things I want us to note here, that the angle c is always read from the positive real axis. So the angle c counts from the positive. Let me redraw this here. Take note of this, where we are going to be dwelling on this part. Assuming we have our complex number z to be this, the angle reads from positive real axis to wherever our complex number is, and this is angle theta. Take note of this. So also, if you have our complex number being drawn on this particular quadrant, we are going to read our angle from positive real axis down to where we have our complex number, and this will be the angle theta. So this is the angle we are looking for, and that's the angle that we call the argument of the complex number. Now let's look at the properties of complex number. I'm sure by now that looking at some properties of some basic parameters is no longer a new thing in this series. We have been looking at properties of a lot of things, modulus. We look at properties of modulus, properties of conjugates, properties of complex number, properties of argument also down. So just get used to it. We'll be looking at properties all through this series. So now we have only two properties for argument, also known as the amplitude of a complex number. And the first one, just like I represented before, I think I've mentioned this, that we represent the argument of a complex number by arg. So if you're looking for the argument of complex number z, we represent it as argz. So this is argz. So if you have arg, which is the argument of complex number 1 multiplied by complex number j, zj. So this is also the same as saying arg z1 plus zi plus arg z, that is not 2, that's supposed to be j. So I'm going to change that to j. Okay, so j. So this is the first one, and the last one, which is the second one, is if you have division arg Oh, that's too big. I'm going to clean this off. So arg zi over zj, this is equal to arg zi minus arg zj. So what this means is that if you have two complex numbers zi and zj, and we take the argument of, and we multiply those two complex numbers by each other, we take the argument. It's also the same thing as finding the argument of zi and adding it with the argument of zj. Take for example, if you have zi, which is defined as 2 plus 3i, and zj, which is defined as 4 plus 5i. If you're looking for the argument of zi multiplied by zj, this is also the same as finding the argument of zi and adding it with the argument of zj. Second one, which is the argument of division. If you're looking for the argument of zi divided by zj, this is the same thing as finding the argument of zi and subtracting the argument of zj from it. So these are the two properties of argument that we're going to be working with in this tutorial. So we have seen the basic introduction to argument. We have seen the meaning of amplitude, which is the same thing as argument. We have seen the properties. Now let's start looking at some examples. Okay, I forgot to make mention of this, that we're going to be having theta, which is our argument, as tan inverse of y divided by z. So y still remain the imaginary part and x still remains the real part, while looking at the complex number z equal to x plus I y. So we have the real part to be x and the y part to be the complex part. So take note of this. You don't need to cram this. Once we start looking at some examples, you see that this is quite easy to work with. You don't need to cram. There's no any formula we have to cram. You can just have to recall some of the laws of trigonometry, the sine, cosine, and also the tangent. We're going to be using majorly the tan. We won't be using sine and cos. We'll just be using tan or true while finding the amplitude of a complex number. So take note of this, that we have theta to be equal to tan inverse of y over x, and we have y to be the imaginary part and x to be the real part. Now let's start looking at some examples. Okay, let's get to it. We're going to be starting example now, which is the first example we're going to be looking at in this tutorial. Looking at it, given that z1 equal to 2 plus 5i, z2 equal to minus 5 plus 4i, z3 equal to 2 minus 3i, and z4 equal to 7 minus 5i. Plot the complex number on the Argand diagram and find the modulus and amplitude, same thing as argument. So let's look at the questions that we have to solve in this particular problem. We have to plot the complex number on the Argand diagram, and we have to find the modulus and amplitude. So we'll be looking at Argand diagram, and last tutorial we look at the modulus. If you are not used to modulus, feel free to check out the last tutorial on modulus and conjugate of a complex number. And we'll be looking for the amplitude, which is what we look at in this tutorial. So let's get started and get this with. So the first one is z1 equal to 2 plus 5i. So the question here is to plot this on the Argand diagram, and also if you find the modulus and amplitude of this complex number. So the first thing I'm going to do here is to plot this on the Argand diagram. Now this is the real axis and this is the imaginary axis. So we have 2, which is the real part, so we can choose 2 to be A, and we have 5, which is the imaginary part, we can choose 5 to be A. So let me use a more vibrant color. Okay, so let's say this a complex number z1 equal to 2 plus 5i. Now when I was mentioning concerning arguments, I said we always read the angle from the positive real axis. So our theta starts from positive real axis and goes to where we have our complex number. So we have angle theta here. But before we find angle theta, let's do some other question, which is to find the modulus of this complex number. So this, we are done with plotting this on the Argand diagram. This is what we have to do by plotting it on the Argand diagram. Now to find the modulus of z1, we look at this in the last tutorial. We take the square root of the real part squared plus the imaginary part squared, and from here we have that this is equal to root of 34. Now to find the argument of this complex number, we're going to have that tan theta. Now, if you look at this, we have a trigonometric expression here. So let me just bring out. I'm not going to do it for every other question. I'll just do it for this one so that we have clear understanding of what we have to do when we have to find the amplitude or the argument of a complex number. So let me bring out this triangle. I have this. So it's a right angle triangle. This is angle 90. This is theta. And if you check, this side equal to 5 and the adjacent equal to 2. So adjacent is 2 and the opposite is 5. So if I have to find the angle of theta from our trigonometric identity, we have that tan theta equal to opposite, which is 5, over adjacent, which is 2. So here we have that theta equal to the tan inverse of 5 over 2. And then we have theta equal to, that is 59.04 degrees. And this is the argument of the complex number z equal to 2 plus 5i. So I wanted to take note of something, that while looking for our angle theta, we start reading the angle from the positive real axis and we move to the angle up to where we have our complex number. So we're going to be using this principle in all the questions we're going to be solving in this particular example. So let's move to the second example. We are going to get this better. We have the complex number z2, which equals to minus 5 plus 4i. Minus 5 plus 4i. So as I did in the previous example, previous question, we have to plot this first on the Argand diagram. So this is the real part and this is the imaginary part. Now here, if you notice, we have the real, our real part is in the negative axis, so we have here to be minus 5. I'm going to put it at the lower part. We have minus 5a, and our imaginary part is in the positive part, so we still have 4a. So plotting this, so we have the complex number z2, which equals to minus 5 plus 4i. Now, if you have to take our angle, which is the argument of this complex number, we are not going to take the argument on this side and name this theta. No, this is wrong. So what we have to do, as I mentioned initially, is to read our angle from the positive real axis. So we read our angle from A. So this is the angle we are looking for, theta. So we are looking for this angle theta, but we can't find this angle directly, but we have to find this angle also, and I'm going to name this beta. So it's very easy for us to find beta, and don't forget the angle, the sum of angle on a straight line is 180. We can subtract beta from alpha. We are going to have that theta equal to 180 minus beta to get our angle theta, and theta is the angle that we are looking for, which is the amplitude of this complex number. Okay, let me just proceed with that. If you study this triangle again, we are going to have that tan beta equal to, here we have opposite to be equal to 4 over the adjacent, which is 5. So we are not going to consider the negative sign, and here we have beta equal to the tan inverse of 4 over 5, and we have beta to be equal to 38.66. So this is 38.66 degrees. And from there, since we know that this is 38.66, we can subtract 38.66 from 180 to get angle theta. So theta equal to 180 minus beta, which is 38.66. And we have that theta equal to 141.34 degrees. 141.34 degrees. But recall, there's one thing we are supposed to do in this particular example, which is to find the modulus of this complex number. So I'll just do that here. So z2 equal to the root of negative 5 square plus 4 square, and this is equal to the root of 41. So that is that with the example number 1 and example number 2. So I want you to note something here. In the last slide, I mentioned that theta equal to tan inverse of y over x, and I said Y is the imaginary part while X is the real part. So looking at this particular formula, if you come down to where we are finding our amplitude, you can see that here we have theta to be equal to tan inverse of 5 over 2. If you look, sorry, this is the Y part and this is the X part. So instead of going through all this stress, you can just know that our theta is equal to what? Tan inverse of Y over X. So it can be applied, but it's very good to draw out your diagram in all cases. For example, in this case, if you just take tan inverse of 4 over 5, you can get the answer directly. This is what you're going to get, whereas our theta is equal to 141.34. So let's look at the third example as we round off. So the third example, we have that our complex number z3 equal to minus 2 minus 3i. Minus 2 minus 3i, this is going to fall on the third quadrant. And if you plot the Argand diagram, so both the real part and the imaginary parts are in the x part. So we have the real part and the imaginary axis. So we have -2, which is our real axis, and we have -3i, which is the imaginary part of the complex number. So if you trace this point, we are going to have this to be our complex number, and we have that z3 equal to -2 minus 3i. So I won't skip this again. The first thing we have to look for, let me just stop this for now. So what will be the angle that we are looking for? The angle theta. It's this angle. It starts from the positive real axis and you trace it down to where you have your complex number. So this is the angle we are looking for, angle theta. So that is our diagram. Now let's look at the modulus of this complex number. We have modulus of z3 equal to the root of -2 square plus the -3 square, and this is equal to the root of 13. So that's the modulus of the complex number. Now let's look at the amplitude, which is also the argument of the complex number. Now, what we have here, we have theta, which we can calculate directly. Also, we can calculate directly, but it depends on your knowledge of trigonometry. So, what I'm going to do here is to find this angle. I'm going to name it beta. So I can say that tan beta. Let me change this to a more vibrant color. We're going to have that tan beta equal to the opposite, which is in this case 2, over adjacent in this case, which is 3. So don't forget to neglect the negative number. And then we are going to have beta to be equal to 33.69. So we now have beta to be 33.69. So initially, don't forget that this angle is 90 degrees. This angle must be 90 degrees also, and this angle must be 90 degrees. So if you sum all these together, you must have 270 degrees. So therefore, subtracting our beta from 270 degrees, we are going to get the angle theta. So theta equal to 270 degrees minus 33.69 degrees, and this gives us that theta equal to 236.31 degrees. So this is the argument of this complex number, 236.31 degrees. Now moving to the last example, I'm going to go up and clean some so that we can have more space to work with. So I'm going to clean off the first. So let me erase this. So we're going to have more space to work with. Now, the last one, which is the fourth. We have number 4. Complex number. Z4 is defined as 7 minus 5i. By now, I'm sure you have gotten the gist of how we're going to be finding the amplitude of our complex number. So, as always, we draw the Argand diagram first. Oh, that's not good. So let me erase this. Oh, why am I drawing the same thing? Let me try and draw, okay? Yes, I got it this time. So this is the real part and this is the imaginary part. So we have our real part for this complex number to be positive, so this is 7, and the imaginary part to be negative. So this falls to the fourth quadrant, which is negative 5. So we can trace this and draw out our complex number. So we have Z4 to be equal to 7 minus 5. Right. So this is our complex number, and this is Argand diagram. So the angle we are looking for is the angle from the positive real axis to where we have our complex number, and this is theta. So the next thing we have to do is to find the modulus, as the question states. We find the modulus of this. So this is the square root of 7 squared plus negative 5 squared, and we have this to be the square root of 74. So this is the square root of 74. Now moving to the amplitude. As always, we are going to take this to be our beta, and from here we have that tan beta equal to opposite, in this case is going to be 5 over adjacent, which is the imaginary part over the real part, which is 7. So we have beta to be equal to 35.54 degrees. And now how do you find, don't forget you have this 90 degrees, this 90 degrees, 90 degrees, and 90 degrees. So sum of angle at the point is 360 degrees. So to find our theta, now just simply subtract beta from 360 degrees. So theta equal to 360 degrees minus 35.54 degrees. So let me clean this side. So we have theta to be equal to 324.46 degrees. So this is our angle theta, 324.46 degrees. So I'm glad to have come to the end of this tutorial. But before we go, I'd like us to try I would like you to try this, and feel free to post the answer in the comment section below. I'm going to give an hint on how it's going to be solved. So say we are given that Z1 equal to 2 plus 3i. Also Z2 equal to 4 minus 5i. So we should find the modulus and the argument of Z1 plus Z2 over Z1 minus Z2. So how do we go about this? Do this and feel free to post the answer in the comment section below. So we have looked at the division of complex number. What we need to do first here is to add Z1 Z2 and also subtract Z2 from Z1. Then after that you can go with realification, which is the division of complex number. You try to treat it as if you are doing rationalization of sort, and then you can do your division. Then you get a single and a linear complex number. From there you can find the modulus and also the argument. So that's that concerning this tutorial. In this tutorial we're going to be looking at how to convert complex number to the polar form. I promise you this is going to be amazing. A lot of work we have been doing with a lot of hard work. We have been doing division with a lot of hard works, multiplication with a lot of hard works. If we can convert complex number to the polar coordinates, everything is going to become easy. So stay tuned and don't forget to watch this tutorial and also the next tutorial. If you like this video, feel free to share, like, and also subscribe to the channel so that you keep updated as I'm releasing all the content. So bye and see you in the next tutorial.